They bring back that one.
I'm joking for Kim.
They bring back that one series that would show some things like blackout.
That's gonna be me.
Okay.
That's
So-
actually my future plan. My future plan is to go across the United States and show up to every UN meeting.
I think you should.
Okay. So here's the fourth and final possible combination. We had a delta H of negative 30. Delta S is positive. We're looking at two different temperatures, 2 Kelvin and 4 degrees Kelvin. Which term is driving it towards spontaneity?
Delta H,
Why?
because it's exothermic.
It's exothermic. So Mother Nature is liking this, like, hey, it's an exothermic reaction, okay? So the enthalpy part is good. But why doesn't she like the entropy part?
Wait, no, she does like the intro. Because we're gaining.
Because shouldn't it be minus bird?
Yeah, right.
Oh, it is minus, my
Okay.
bad.
That's what I was confused.
Okay, my bad. That should be minus.
Come
Okay,
on,
back off
you're
me,
fine.
okay?
He's just having some fun.
He was making sure we were paying attention right now. He was making sure.
He was trying to make sure we were paying attention.
Okay, minus. She doesn't like the entropy term because that is showing a decrease.
Yes.
So it's warm, but she's got to clean. Okay? Not horrible. So you go back to the basic idea. So I got negative 30 minus, and we'll start with the 4, times the negative 10. Okay? Joules per mole, kilojoules per mole.
Oh, wow.
So I got minus 4 times the negative 10. So what am I going to do mathematically, ending up with that term over there?
Positive.
Positive. So I'm going to have negative 30 plus 40, which is going to get me,
10.
Yes.
so my delta G is going to be a positive number. So is it spontaneous? No. So what's happened is that I've let the T delta S term get too big, okay? Now, I'm gonna do the same thing, but now I'm gonna lower the temperature to 2 degrees Kelvin. So now I've got negative 30 minus 2 times negative 10 kilojoules per mole Kelvin. Now what do I get? I get negative 10. So now that's going to be spontaneous. So if I'm too warm, it doesn't happen. But if I'm colder, then it does. So what that tells me is there's a break point. There's a temperature where this can become critical. So if I look at this, what we did up here, and go, okay, hey, if I look at delta G equaling 0, and then delta H minus T delta S, and I move this over here so I get T equals delta H minus or over delta S. So if you look at the values that you've got, so your delta H is negative 30 kilojoules per mole. So if my delta S is negative 10 kilojoules per mole Kelvin, the critical temperature is going to be 2. So if I'm at 2, the system's in equilibrium. So, what? 3. I'm sorry. 3. I was thinking 2 we just did. 3. 10 divided by 30 divided by, you all are looking at me, it's like, okay, what did I do wrong? So, at 3 degrees Kelvin, the system's going to be in equilibrium. So, what I was thinking. So if I drop it to 2, okay, so if I go below that point, then I let the enthalpy term be dominant, and I get a spontaneous reaction. But if I run it at too high temperatures, my entropy term becomes dominant, and it drives it away from spontaneity. So this is why when you have a negative delta H and you have a negative delta S, so that's dependent upon low temperatures. So one way that you can remember this, and if you have a positive delta H and a positive delta S, that's dependent upon higher temperatures. So one way you can remember this in terms of just like human interactions, if people are positive, hey, that tends to raise you up, okay? Like, oh, I feel better about life, okay? Raises your spirits. If people are negative, guess what? It's like, oh, that's depressing. Hanging out with that negative person is like, oh, that's just sad, okay? And it lowers it. So that's an easy way to remember this. So one of the things, this is the next set of things that you have to know without hesitation. If you're into flashcards, I'd make one for what happens, the conditions for it always being spontaneous, never being spontaneous, conditions for high temperatures, conditions for low temperatures. And again, when I say high and low temperatures, that's a relative value. It's just above a certain temperature. It doesn't have to be really, really hot, okay? It just has to be above a certain point. If you're a math nerd, okay, your temperatures for this to work, the Kelvin has to be positive value. So the only way, if you look at T delta H over delta S, the only way you can find a critical temperature is if they're either both positive or if they're both negative. Okay, that's the other way to go, hey, is this going to create a temperature critical situation? If those have opposite signs, positive delta H and a negative delta S, you cannot find a temperature that satisfies that requirement because you can never generate a negative Kelvin. So you can look at it mathematically, you can look at it in terms of Mother Nature likes a hot mess, exothermic, endothermic, positive entropy, negative entropy. Doesn't make any difference. Just find a system that works. Okay. So if you look on the lecture notes that you've got. Nope. So, for reactions that are spontaneous at low temperatures, delta H is blank, delta S is blank. Positive, negative. Negative and negative. Spontaneous at high temperatures, and I even gave you a little visual clue there. That's going to be positive and positive. Reactions that are always spontaneous, delta H is negative. Delta S is positive. And if they're never spontaneous, delta H is positive. Delta S is negative. Okay. Now, here's how this plays out. Okay? This is for basically melting ice, changing it from solid into the liquid. So let's look at the big idea. Here's the values for delta H. Here's are the values for delta S. Graham, why is delta H positive for melting ice?
Because it's endothermic.
Why?
Because you need energy to break the bonds.
Beautiful. I got a positive delta H. I got to put energy into the system. Okay? Mother Nature is going to get cold. She's not liking it. Gap Sean, why is delta S positive though?
Because it's going from a solid to a liquid.
Yeah. So, which is driving it towards spontaneity? The enthalpy term or the entropy term? Entropy, but enthalpy is driving it away. So I've got two positive values. Spontaneous at high temperatures, spontaneous at low temperatures. High. So the temperature has to be above a certain point, right? Okay? And that temperature is going to be 0 or 273 Kelvin. So if you want to calculate delta S from the surroundings, you take the sign of delta H and you switch it and make it, in this situation, negative. and you divide it by the temperature. So to save you some time, I went through and I did these calculations. Well, it's just more than enough time, so,
He doesn't actually.
It
It
was
wasn't
out of time.
Don't get it twisted.
yeah, don't, let's not read too much into this.
What number is that?
I hate this thing. I hope the Easter Bunny brings me back in.
I will.
Are you the Easter Bunny?
Yes.
No way.
I'm not supposed to outgain what? I don't follow.
Those are Jewish criminal
That.
Okay, now, why does delta S from the surroundings have a negative value?
Because the ice is outside energy in from somewhere.
The ice is taking energy in from somewhere. That's the whole point of putting ice in a drink. From an entropy standpoint, what's the role of ice? To lower the entropy of the drink. Okay? It's like, I need ice, I need to lower the entropy of the drink. Most people look like you're crazy, but if they understand chemistry, they go, oh yeah, that's cool. Okay, now, delta S for the universe. Here's where you have to pay attention to the units. This is in joules per mole Kelvin. The system is also in joules per mole Kelvin. We can just add this together. So if you do this, this is negative 0.8, this is 0, and that's positive 0.8. So let's focus on the first one. You have a negative value for the change in entropy of the universe. Is that spontaneous or not spontaneous? Not. Because for a reaction to be spontaneous, what do you have to do to the entropy of the universe? Increase it. Not happening. It's negative value. Guess what? We're at 263 Kelvin. That is minus 10 Celsius. Ice is not going to melt. You're at 273 Kelvin, otherwise known as zero. Whoa. Now we're at equilibrium. Okay? So that's that phase transition. You go to 283, which is 10 degrees Kelvin. Delta S switches to positive value. Okay? Now, if you do the T delta S term, so here's a decision that you're going to have to make. That T delta S, notice that your delta S is in joules per mole Kelvin. In this case, your delta H is in joules per mole Kelvin, so they're all in the same. But a lot of times when you're given thermodynamic data, your delta H is in kilojoules, and your delta S typically is in joules, because your delta S values are smaller. So you need to make a decision, hey, make them positive or negative, whatever. So, oddly enough, when you add these together, your delta G at 263, is your delta G going to be a positive or negative value? Positive value. At 0, what's going to be the value of delta G? 0. And at 10 degrees, you're going to have a negative delta G. Okay. Kevin, stop you under camera for one more time, and then we're good.